And then number 12, the last problem. Well, 12, 13 are combined. It's probably the hardest of the batch. And when they ask you, by how much does the ball clear or fall short of clearing the crossbar? It's a football kick. See if he gets a field goal. They're asking, that's a why question. When it says, how far does it clear or fall short of clearing, what they mean is, all right, the football is either going to clear or fall short, and that's a why question. All right? That's what they want to know. All right? So it was a little confusing when you first read it. Okay, it's time for us to move on. We're going to move on to Newton's laws. Quiet, please. Yeah, there was a girl in class one time, and there was an ice storm. We didn't have school, and she comes back the next day. She goes, "Oh, Mr. Bruin," said, "you won't believe it." She said, "Physics has ruined me." And I'm like, "What?" She said, "Because I'm driving along. My dad's in the car, and he's letting me drive on the ice, or we drive the car even though it's icy. So I'm driving it, and we're taking a turn, and we hit an ice patch, and we start to slide." And I don't remember saying this, but my father said I was screaming, "Too much momentum, not enough friction. Too much momentum, not enough friction." And I'm like,
wow.
Yeah. Yes, you're dreaming physics. It's awesome. Your life has now become opened up to a larger universe. Your life is complete. Oh my God. Okay, here we go. We're starting something new. We're starting Newton's law. Let's go way back.
No.
Way back. Galileo.
Whoa.
Way back.
The original ocean.
All right, Galileo ran an experiment where he had a marble, sphere, something, in a bowl, okay? And he lets this thing go, and it goes up the other side. All right, well, how far does it go?
As far as it wants.
Really?
As far as Josh Hamilton.
As far as momentum takes it.
Come on, seriously. Quit jerking me around. How far does it go?
If there's no friction?
No, we have
I'm pretty sure.
All right, well, how far would it go with no friction?
All the way back and forth, back and forth.
Same height.
It's conservation of energy.
Same height. Well, that's the deal. He's the first one that comes up with that idea. Because it's like it rolls to the other side, and it goes over here. So it's like, okay, well, he polishes this off, makes it smoother. So it goes higher. All right? But he can never have it go the exact same height, but he gets pretty close. And so he comes up with this idea of, well, if you're in your imaginary frictionless world of science, all right, then this thing would go to the other, all the way to the other height, the same height, okay? And his terminology was something like it would seek the same height, all right? That the object would continue to move until it reached the same height it was originally, okay? And to test this idea, you can do this. You can have a long bowl and see where it goes. And he discovered that really, if you had very little friction, nice and smooth, that you would get to the same height no matter what the shape of the bowl was. All right? And so then he goes, wait a minute. What if your bowl was shaped like that? That is a bowl. It's a one-sided bowl.
That's not a
That's
a spoon.
It's known as a ramp, probably, right? So the ball rolls down the ramp, one side of the one-sided bowl, and if this ball continues to roll till it seeks its same height,
It'll never.
It'll go forever.
his idea was that it would go forever. Okay? And so it's the first concept of this idea of inertia. And actually that's where he goes with it, is he said, he went one step too far. He said, look, he said this object will seek its same height. It has this property called inertia. Object will keep moving. All right? Until when? Well, until it gets to the same height. And so he said, well, all right, so it'll go on forever. And they said, yeah, but this is on the earth, right? So here's the ball in our one-sided bowl. And it will roll all the way around the earth.
Orbit.
Yeah, kind of like an orbit. So he went one step too far. He said natural motion will be in a circle. All right? We know today that natural motion, the motion not influenced by any outside forces, is not a circle. Okay? A force is required to cause something to go in a circle. What's the force that causes this ball to go in a circle? Centripetal force. Oh, no, not the dreaded centripetal force. There's no such thing as centripetal force.
Centripetal acceleration.
Centripetal acceleration, that's not even a force. Centrifugal,
You're not separating anything.
leave. Don't come back.
That's chemistry.
Bring a TV.
There's no such thing as centrifugal force. All right. There is, a force can be labeled as centripetal, but centripetal is not a magical new force. What is the real force that causes this ball to go in a circle around the earth?
Gravity.
It's gravity. Okay? Because gravity is keeping the ball on the earth, right? Okay. No orbits without gravity, right? Turn gravity off, all the satellites float away. The moon floats away, right?
Who turned the sun
The
off?
sun floats away. We all float away.
We would float away. Actually, everything would float away.
Where would we float to?
That way.
I thought that.
Okay.
I float anywhere.
Whatever your name.
Yeah, but I would float that way.
All right, enough silliness. So, the first idea of inertia comes about from Galileo. All right? Newton didn't invent that idea. As far as we know, Galileo invented the idea of inertia, that an object will continue to move if it's not influenced by something else. All right? So, let's go on. Newton grabs hold of this idea and he graduates the idea to something a little bit more broad. We come up with Newton's first law. Okay? Okay, you all heard Newton's first law before. What is Newton's first law? Very nice. That was totally wrong. Let's do it again.
You were asking for it.
For every... No, that's not right. I almost did third law. An object in motion remains in motion, and an object at rest remains at rest unless acted on by a net external force. Okay? Now here's the deal. I want you to modify that slightly, okay? An object in motion will stay in motion, and what kind of motion is that motion? Constant what? It's in straight line, linear motion at the same speed. Okay? So natural motion for the universe is constant velocity motion. Alright? Everything in motion stays exactly the same speed in exactly the same direction unless you do something to it. Okay? And now on Earth we never really see that, because we just talked about trajectory motion. We always have gravity. So when we throw something through the air, it doesn't keep going in the same direction. Even if you throw it really fast, it's in a parabola. Okay? The only time we see things that resemble this type of motion is if we can eliminate gravity. So like, for instance, if you've ever been, played air hockey. Okay? You have gravity down, but the air pressure up on the object produces a force up that cancels gravity, and there's very little friction, so the object in motion stays in motion, right? Or if you've ever been in a car on a patchy ice patch, an object in motion stays in motion no matter what you do to it, right? Okay, because if there's no friction, you can't get it to turn. You can't change the motion of the car. Okay. All right. So we don't see this very often here on Earth because we have gravity. Out in space, that's exactly what happens.
Have they tried it in space?
Yeah, sure. They have. I need to download some videos of like stuff from the space shuttle and old Skylab videos and things like that. Because in space, it's really cool. In fact, I just had a colleague that went on the shoot. What's it called? The Vomit Comet, the plane that takes you through the parabolic arc flight, and you have about 30 seconds to a minute or so of zero-G behavior, and so floating around, things fly through the air in a straight line. There's videos of this. I need to download some of these for you, because in space, everything, once you let go of it, like in the shuttle, when you're in free fall around the Earth, you throw something across the shuttle, it just keeps going. All right? It's really cool. So, you can launch yourself from one wall and shoot straight across to the other wall. It's really neat. Yeah. So, inertia. Inertia is this property that objects have. Inertia is not a thing. It's this idea that objects in motion stay in motion. We call that inertia, that objects have inertia. Okay? We measure inertia with the number mass. Okay? Mass is a numerical quantitative value for inertia. And your mass depends, so therefore your inertia depends only on the number and type of atoms you have. And that's it. Okay? So if you go from here to the moon or to someplace else, your inertia does not change. Your mass doesn't change. Because the number and types of atoms you have don't change as you go someplace new. All right? So there you go. Newton's first law. By the way, NASA uses this idea all the time. When they send a rocket ship to Mars, okay, they don't keep the engines running on the ship all the time. Yeah, all they do is they just use the rockets to get it up to speed, and they point it in the right direction, and they shut it off. And they coast all the way in. Okay, it's like a really long pass pattern. Mars is coming around that way, and they throw the ship over there to a point in space where Mars is not. And then they meet. It's a really cool little mathematical problem. That's right, and then they run it in for a touchdown. And they have to hit Mars at just the right angle and speed, because if they don't, then they can't get into orbit. So they have to calculate all that stuff out in advance, and the only thing they use the rockets for is just to adjust it as it goes through space if they're off by a little bit. Okay? All right. Now, let's make sure we got this right. Let's say we're looking straight down at a table, and you have like a tube. This tube is shaped like this, and you shoot a marble into the tube this way. So the marble comes out of the tube over here. And we're looking down at it from the top. All right? So, here are your options. A, B, C, and D. When the marble exits the tube,
Is there gravity or not?
there is gravity, but we're looking down on it, like it's on the floor. And we're looking down on top of it. Okay? So it's a top view. Marble comes out the tube at the end. Which path will it take? A, B, C, or D?
B or C?
B, I think. Or maybe C.
What's inertia tell you?
B.
An object in motion, when it exits, which direction is it going? As it exits, it's going this way, right? With velocity, and an object in motion will stay in motion, right? Okay, so like for instance, let's get out that. All right, let's say I got this.
Oh no. What is that?
Again.
Hit you again? All right, I won't hit you again.
Oh my God.
Watch out, it's getting close. Whoa, hey, ow! Watch out. Be careful, you're gonna hurt somebody. Okay. All right, so let's say Daniel's irritating me today.
Oh, just.
We're gonna do it now.
What's that? Now?
Now.
Now?
Now.
Now Elisa's irritating me. If I want to hit Lisa with this,
Now.
when do I let go?
Now.
Because Lisa's back there.
Now.
Go.
So, here,
Now.
if you've ever done this as a kid, the first time you let go,
You miss.
yeah, you let go when it's right here. Because Lisa's back there, so it's coming around this way, and you say, oh, I let go right there. Where does it go? There.
It hits.
Because once you let go of it, an object in motion stays in motion, right? Yeah.
Isn't it like a sport where you throw around with something heavy and then you just like launch it off?
That's called the hammer throw in the Olympics. The hammer throw is, yeah, they've got like a, gee whiz, I don't know, it's like 16 pounds or something, some ridiculously heavy steel ball on the end of a chain, and they spin around with it, and then they have to throw
Oh,
it.
yeah.
Matilda.
Oh,
What's
yeah.
that?
Miss Trunchbull Matilda, she grabbed the girl
Oh.
by her pigtails.
Yes, that's right.
I can't believe you remember the name.
Okay, so tell me, if I want to hit Daniel, when do I let go?
What was the teacher?
Now.
Now.
Now?
You'll hit me
Now.
first.
Now? Oh,
Oh my god! It worked.
That was
it worked.
I haven't hit you.
All right?
Nobody hit
Now, it takes a little practice to get it right. Lisa, you back there?
I think you're gonna hit Ian.
Now. Now.
That's all right. Ian already hit me. When?
Now. Now. Now.
Now. Hang on.
Faster.
When?
You were trying to hit.
Now?
He said
Now? 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 Here, let me give you a new way to think about trajectory motion.
Okay.
Car. Going off cliff.
Why?
Velocity.
Why is everybody driving off a cliff?
It's been a bad day.
They can't walk off a
Okay,
cliff.
object in motion stays in motion. Object in motion stays in motion unless acted on by an outside force, right? Our outside force is gravity. And so what happens is, instead of going straight, it falls because of gravity into this shape, right? Okay, now, but what if you launch off this way? Then you should go straight.
But there's still gravity.
We're still going.
But there's still gravity, and you know what? If you travel here the same amount of time and distance, you'll fall the same amount. If you're in the air the same amount of time, you'll fall the same exact distance. It's just that it's going to be in this parabola instead of this parabola. Okay? The same exact fall. All right? And if you let go of the object right here, the same amount of time, it falls the same amount of distance. So as long as the time is the same, this y fall is exactly the same. So you have the exact same force on the exact same object. Does that make sense? Okay, there are four, hang on, four, count them, only four forces in nature. All right? Do you know what they are?
Gravity.
Very good. Gravity is one.
Magnetic.
Magnetic? Magnetic, let's add something to the front of that.
Electromagnetic.
Electro.
What are we at?
Electromagnetic. Hey, very good.
What?
The nuclear strong force
And the nuclear weak.
and the nuclear weak force.
What are these again?
They're the forces.
Yeah, these are the only four forces in nature. Okay?
Oh.
Yeah.
Now let's try combining them.
Yes. Actually, they have. That's what they're trying to do, is find out if they are all come from one single force. They've been able to combine the electric and weak force. I don't know if they've gotten all the way to connecting.
They got the three except for gravity.
Yeah, except for gravity. This is the. I forget what they call this one. There's a name for it.
The awesome force.
grand unified theory or something for these three. And then to combine them all, it's
supposed to be small. If I invent a force, I'm just going to call it
all right, now, everybody, look. All forces you can think of are one of these. Okay? Friction, yes, is one of these. In fact, here, let me eliminate two. Because all forces you can think of are probably not going to be one of these two. The strong force is what holds the nucleus together. So you've got the nucleus, which is made up of protons and neutrons. And protons and neutrons, particularly the protons, have a plus charge, right?
Yeah.
So they should repel each other, right? So the nucleus, which is made up of a bunch of bunch of pluses, yuck, made up of a bunch of plus charges and neutral charges, it should repel itself, right? It should fly apart and disintegrate. But there is a force that holds it together, and that's called the nuclear strong force. The nuclear strong force actually attracts or repels depending on the location of the objects. All right? Like for instance, if you have a proton here and a proton here, as you bring them closer together, the strong force actually repels, and then when they get to just the right distance, it attracts, and when they get too close, it repels again. Okay? And that there's a sweet spot where it is just the right amount of attraction before it starts to repel, and that's the difference in between these two. The difference between the protons, that distance, is where they normally will stay. All right? It looks like this.
I saw it fall.
Okay. Positive force means repel, negative force means attract. So if I have one proton right here and I bring the other proton in, it's repelled. This actually drops off to zero. It becomes repelled, and then when you get to this spot, it starts to become attracted, and so it will fall into this region right here where it's attracted, and they'll stay together in the nucleus. But if they get too close, they're repelled apart. So it's this is the sweet spot where they will stay. They'll attract, and if you can get them that close, they'll merge. So like this is what they try to do in fusion. In fusion, they got to get a proton past this repulsive part into this area here where they will attract, and then they will merge to make, like two hydrogens make a helium. Okay? All right. Now, there is another force that's like a repulsive force. It's the weak force. This is the force that causes radioactive decay. So if it wasn't for the strong force, we wouldn't have any nuclei. All right? We would disintegrate into quark dust if it wasn't for the strong force. That holds it all together. The weak force is what causes the nucleus to fall apart. Okay? Now, that seems kind of odd. Why would we want the weak force? But the weak force is responsible for all nuclear reactions, like nuclear decay, things like that, and fission. And if without that, then we wouldn't have solar radiation from the sun. So we like the weak force as well, because that's what causes our sun to be able to emit energy. All right? But these forces only act over a really, really small distance. Come on, Lisa. Stop. Only act over a very small distance. Like about the width of the nucleus is all that they will do. Anything beyond that, it drops off to zero. So in the world we live in the big world we live in, outside of atoms, okay, then these don't play a part in our daily life. Okay? So that means everything else in our daily life is either gravity or electromagnetic. Well, gravity holds us to the earth. Does gravity attract you to people out in the hallway?
Yes.
Yeah, it does.
Yeah, it does.
Physically attracted to people in the hallway.
But it's really, really, really small force. I mean, you don't walk down the hallway and stick to the wall, right?
I do.
Because of gravity.
If you walk by Johnny.
Yeah. walk by someone and smack, you're stuck to them. All right?
Johnny just walks around with people stuck to him.
That's right. The more mass you have, the more attractive you are. Because of gravity.
Johnny!
Okay, so wait a minute. So if that's all that gravity does, gravity and the electromagnetic force act over an infinite distance. But gravity only attracts. That's all it does. Okay? Gravity and electromagnetic act over an infinitely far distance. These only act around in the nucleus. So everything else that you can think of is the electromagnetic force. Friction, tension, normal force. All those things are all the electromagnetic force. Okay? So like when you run down the hallway and you're not watching where you're going and you run into the wall, that force you feel when you run into the wall, that's electromagnetic. Okay? Now, why is that? What are you made of?
Water.
Water?
Which have electrons.
Mostly water. Protons and electrons, right? You're made up of atoms. Okay, how are the atoms arranged?
Like this.
In the shape of a person.
How are atoms arranged?
Electrons on the outside, nucleus, protons on the inside.
You've got a nucleus, and then you've got the electrons out here doing their little electron thing. Okay? In a big cloud of electronness on the outside. So when you run into the wall, what part of the wall do you hit first? Electrons. And what part of your body hits the wall first?
Electrons.
So why don't you just run through the wall? Because you know atoms are mostly empty space. Why don't you just pass right through? Yeah, because your electrons that cover your body are repelled by the electrons in the wall. And so your electrons and their electrons repel. Okay?
So why don't we just like bounce off of chairs? So you can like go.
So why don't we just bounce off of chairs?
Gravity is stronger.
Now if you...
There's enough force you could actually balance.
Yeah, if there was enough force, you could actually bounce. So like for instance, if, like Greg, I'm not bouncing off the wall, right? But the wall's repelling me and the floor is repelling me, right? And the chair is repelling you. What's really weird is you're not really touching the chair that you're
I thought we
sitting
already
in.
went over
So
levitating.
many electrons, I cannot punch him in the
I'm
face.
claustrophobic.
See? You didn't punch in the face.
My electrons.
Right, yeah, the next time you get into a fight, just tell the assistant principal,
We didn't even touch.
I never touched him. My electron cloud, his electron clouds got into my electron cloud space. Right?
Mr. Blue and somebody get into a fight.
No, that I didn't tell you. All right. So there are all of our forces. So like friction and normal force and tension, all that stuff is the electromagnetic force in some variety or another. Okay?
There's electrons.
All right. Well, let's talk about Newton's second law. Actually, you know what? Let's talk about Newton's third law first and show you why, at least with the electromagnetic force, why it has to be. Okay? So let's say that you run into the wall. All right? So you run into the wall, run into the wall.
The wall runs into me.
Or you could say, depending on your reference point, that the wall ran into you. That's correct. Okay, so you're out in the hall, minding your own business, and the wall runs into you. Okay? Now,
Don't be silly.
the wall has electron cloud on the outside. You have electron cloud on the outside of you, right?
Yeah.
So the wall applies a force to you? Why?
Because it repels you.
Okay, because your electrons repel, no, its electrons repel your electrons, right? But can the wall repel you with you not repelling the wall?
What?
Yes.
Yes.
No.
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 Still repellent.
You both have to repel for you to
Equal opposite
I know.
stuff.
hold up.
All right. Is it possible for the electrons in the wall to repel you, but your electrons not to repel the wall?
No, it's impossible because then the wall will go right through you, right?
You would
Wouldn't
be
it
able
just,
to
like,
push the
run?
wall.
You like
That way.
Does it matter whether the wall is moving or you're moving or both moving? No. It just matters at the proximity of the electrons, right? If one electron in the wall repels an electron in you, then that electron in you has to repel the wall's electron back. All right? And so for every force, there's an equal and opposite force. You can think of it this way, too. When you touch the wall, here, everybody, finger, touch the desk. What happens to your skin when you touch the desk? It turns red. Ow, I'm bleeding.
It flattens.
It flattens, right? Okay, what's happening is your finger is made up of a structure that's a solid, a flexible solid, of atoms and molecules connected together. When the electron cloud of the desk repels your electrons, it makes your structure, your solid structure, flex. Okay? When it flexes, because the bonds that are holding all those molecules together gets flexed, it's like a rubber band. And it stretches. And so you get a force back, right? Okay, the same thing happens to the desk. When you push on the desk, it's made up of a structure. Now the bonding that holds it together is more rigid. So it doesn't flex as much, but it still flexes. Okay? So you both flex, you both bend, you're both applying forces on each other. Okay? Here, you do this. Take your two fingers and push them together. You can't push one finger on the other and only flex one finger. Yeah. Even if you do that, they both flex.
Unless, of course, you pull this arm away before you really.
Yeah, but then you're not pushing. There you go, I did it. This is Newton's third law, which is what we're talking about. Newton's third law. First law is inertia, right? Third law is for every force, there's an equal but opposite in direction force. Okay? So write that down. For every force, this is Newton's third law. For every force, there's an equal but opposite in direction force. Now, these two forces never, ever, ever cancel because they always act on different objects. So let's go to our outfielder again. Our outfielder's out, running along, catches the ball, runs into the wall. The wall applies a force to the outfielder. What does it do to the outfielder? Stops them, makes them turn around. What does the force from the outfielder do to the wall? Makes the wall flex, right? Makes the wall shake. Okay, how about this? You've got a hammer. Hammer. All right, so you got a hammer. You got a nail.
Makes a belt toe.
Okay, when the hammer hits the nail, does the hammer apply a force to the nail?
Yeah.
Say yes.
Yes.
Does the nail apply a force to the hammer?
Yes.
Sure.
Say yes. How do those forces compare?
The hammer is bigger.
Ah,
They're equal,
they are equal, but opposite in direction.
but not equal. What about?
Hang on. They're equal.
Now move down.
But
Now bigger.
What does the force from the hammer do to the nail?
Make it more shorter.
Makes the nail go in. What does the force from the nail do to the hammer?
Maybe bounce it. Maybe bounce it.
It bounces it off.
no, it doesn't.
It does something to the hammer because if you swing a hammer and hit a nail, it's different than swinging a hammer and not hitting a nail.
It makes it vibrate.
Yeah, well, if you swing and no.
Yeah, look.
Flex this.
Which way is the force on the hammer? The hammer's coming down. Which way is the force on it?
Up.
Not down. It's going to accelerate. Woo! All right?
I'll throw my foot.
You hit the nail. The force on the nail is which way?
Down.
Force
The
on
force on the nail is which way? Down. And it drives the nail which way? Down. Which way is the force on the hammer? What does it do to the hammer? If you're moving this way and the force is this way, what happens? Slows it down and stops it. Because if the nail wasn't there, your hammer would just keep going.
The wrong way.
Now, here's the misconception. The misconception is that you've learned from elementary school that Newton's third law is for every action there's an equal and opposite reaction. No, 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 no. For every force there is an equal but opposite in direction force. The action and reaction are not the same because the action on the nail is to drive the nail in. What's the reaction on the hammer? To stop the hammer. They are not the same reaction and action. Let me give you an example. Here's you. Here's a car.
Car hits you.
Here's the car flying along and
Splat.
hits you. Okay, answer this correctly. Does the car apply a force to the person?
Yes.
Yes. Does the person apply a force to the car?
Yes.
Yes. If you've ever hit a person,
It screws up your car.
it messes up your car.
I know.
How does the force of the car on the person compare to the force of the person on the car?
It's greater. No, wait.
They're equal.
Car's the person.
Repeat after me.
They're equal but opposite.
They are equal, but opposite in direction.
Yeah, that.
Yeah.
They're bigger, except they're equal. Now, the reason we get the misconception that they're not equal is because of this. Newton's second law.
Second one. Not draw two.
Okay, number one is inertia.
That was the third one, right?
Number three is for every force, there's an equal but opposite direction force.
Oh.
The force from object 1 on object 2 equals the force from object 2 back on object 1, but it's in the opposite direction. They're exactly the same size and exactly in the opposite direction every time. So why do we get this crazy idea that the force from the car on the person is bigger than the force from the person on the car? Here's why. F equals ma is Newton's third law. There's a wording for that if you wish, but it's the easiest way to remember it. It's just the sum of the forces equals ma. The wording is something like, for a net force imparted upon an object, the object will receive an acceleration in the direction of the net force proportional to the mass of the object.
Wait, so here's
Or you could say,
Doesn't make any sense.
the sum of the forces equals ma. No, look. If there's a force on an object, a net force, okay, so when you add up all the forces, the forces don't add up to 0. Because like right now, you're sitting in your chair. The net force on you is 0. So is there an acceleration of you? No. So there has to be a net force. So that means when you add up all the forces acting on the object, there has to be some left over. It has to add up to a value. And whatever that value is, that's going to cause an acceleration. And the acceleration is going to be in the exact same direction as the net force. Always. And it depends on the mass as to how big that acceleration will be. So let's use that over here. What's the mass of a car? Big. What's the mass of a person?
Small.
Not so big.
Wow. Okay.
The force on this object is the same as the force on this object.
The acceleration.
The forces are the same. But if this is a big mass object and this is a small mass object, will they get the same acceleration?
No.
No. Which one accelerates more?
The M.
The small object.
The M.
Yeah, the M. Not the M, but the M. All right? This object gets a large acceleration, and this object gets a small acceleration. Now, which is worse, to get hit by a motorcycle, a car, or a bus?
Well, no, it's on the speed.
Okay, now it depends on the speed of the object, right?
Cycles go faster.
Assuming they're all going the same speed.
No, bus would be better.
Bus would be worse.
Better. He's like better.
You want to be hit
the
by
area is greater, so the amount of pressure on that
surface
certain
area.
area would be less. So it's
Let's
better.
assume all of the vehicles are flat on the front and not pointy. Because if they were pointy, that would be bad.
You're dead right away.
Just jump and I can have.
All right, look.
motorcycle step to the side.
The bigger this mass is, the bigger force capability you get, But since but yeah, you're going to get a bigger acceleration on you, right?
So you're gonna move
Momentum.
faster, hit harder.
Yes. Bigger and bigger and bigger. Look, this is why if you're in a small car and you're in an accident, you'll probably lose.
Mr. Taylor.
Right, Mr. Taylor's little smart car.
That's his?
It's pink.
Yes!
Mr. Taylor's smart car and like a tank, right?
Oh.
They have a collision. Tank wins.
Thanks.
Tank is too slow.
Tank wins because even in a small speed crash, the tank wins because the tank has lots of mass. Okay, say you run a smart car into a bus. Bus wins. Say you run a smart car into a smart car.
Smart car wins.
Smart car wins.
No, both smart cars.
Say you run a smart car into a mosquito.
Mosquito wins.
The smart car wins because the smart car has more mass, right? If you're in a small vehicle, here's the deal. In a collision, the forces between the objects are the same. So the object with the smaller mass will accelerate greater. So this is why you lose if you're in a small car in a crash. Let's think of it this way. Let's say that, all right, you're in your H2, or you're in your smart car.
Sounds like a smart car.
It's smaller than the rims.
By the way, Mike, it doesn't even have that.
That's the scale.
By the way, Mike,
It's a monster truck.
first time we saw a smart car, my daughter, when she was younger, she said it looked like a toddler's shoe on roller skates.
Yeah, makes sense.
All right, when these two collide,
It just roll right under.
here's the deal. Large mass, small mass. F equals ma, but the force on each one is the same. F over here equals F over here, except one's in the opposite direction, right?
Yeah.
But this one has M, and this one has M.
So that one
So
has,
this one has A, and this one has A.
but it's negative A. Large negative.
It's in the opposite direction, right? Now, look. If you're in this car driving, or you're in this car driving, if you're attached to a car with a small acceleration, what will your acceleration be? Small. So what kind of force does it require to give you a small acceleration? Small, right? But what if you're in this car that just received a large acceleration?
Jerks.
You're going to accelerate with that car, right? Which means the forces on your body will be large to get you to accelerate with the car. So that's why when you're in a small vehicle, you generally, all things being equal, will lose. Okay? Now, I'm not saying don't buy a small vehicle. I mean, I still got my old CRX, which is a little two-seater. I drive that thing around, but if I collide with the H2, I'm in trouble. Right? Now, we just covered Newton's laws. Now, there are a few things that are different about the Newton's laws now. Inertia is pretty much the same as you learned before. But Newton's third law, for every force, there's an equal and opposite direction force. Okay, not action-reaction. Action-reaction is not really correct. And then F equals ma. Okay, we're going to delve a little bit into F equals ma here, a little bit more. And we're going to show you the way that Newton actually derived F equals ma. It's not really this. Actually, this is not really truly correct in all situations. Okay, let me show you. Okay. What's acceleration?
Velocity.
Yeah. Now, we don't just do this. Technically, it's dv dt for those of you in calculus. But it's the change in velocity or the change in time. We plug that in. We get F equals m change in velocity over change in time. Okay? Now let's take it back to the way Newton actually described it. And Newton actually described it this way. F equals delta mv over delta t. Okay, what's the difference between these two?
Delta M.
Okay, delta m.
There's no change in mass.
Yeah, over here we're assuming that the mass does not change. All right? Now, there are situations where the mass does change. What's that? Like for instance, if through the day, does your mass stay the same?
Yes.
No, it doesn't.
No.
You start to sweat.
You take a,
You use the restroom.
Use the bathroom.
You eat.
I was gonna say.
Yeah, yeah. You want to lose weight? What do?
Sweat.
You sit there and you don't eat,
And when I eat,
and you'll lose weight.
You're
You
killing
vomit.
really fast.
You go like this.
Stop it.
But you won't have any muscle mass, so it'll be like nasty.
burn calories.
Yeah. You burn calories. You burn energy, right? So you can exercise, you can eat less or not eat, right? And if you don't take anything in, but you are using energy to stay alive, right? Just sitting there, you're using energy to stay alive. All right. So your mass through the day doesn't stay the same. Now, usually your mass doesn't change much, though, right? You eat food, you gain a little mass. You walk around the building, you lose a little mass. Stay about the same. All right, but there are some situations where the mass changes a lot. Like, for instance, a rocket taking off. Most of a rocket's mass is actually fuel, so that when the rocket is taking off, the fuel is being burned up and shot out the back end. So its mass changes a lot as time goes by. So you really shouldn't use this for a rocket, not for the full flight. Now, for one instant in time, sure, if you know the mass at that instant. This is more appropriate. There are other situations where mass is not constant either. If you travel really, really fast, you get some strange effects as you get near the speed of light. Once you get around a tenth the speed of light and start going faster, your mass varies with speed. The faster you go, the more massive you become.
More massive.
More math?
More massive.
So people on a diet shouldn't go fast.
That's correct. If you want to weigh less, stay still.
Don't go. Seriously?
No.
Yes.
No, it's for like
Speed of light.
speed of light.
Yeah.
Yes. We're talking speed of light, though.
But so if I
Very fast.
just check, man.
Okay. So, like, if you would run like half the speed of light, you'd weigh like 30% more or something like that. I don't remember exactly. Yeah. And if you get faster you get, the more massive you become.
You weigh way more. You weigh way more because you have to do a grab.
It wouldn't matter.
Is it that?
You get back.
Let's finish it out. Actually, this is the way that Newton wrote it, which was the sum of the forces is equal to the change in mv. All right? With time. mv is a quantity that they give a name to. It's called momentum. And unfortunately, they name that with the letter small p. All right?
Okay.
I don't know. Because in Latin it's pronounced momentum. I have no idea why it's p. I have no idea.
They run out of letters.
A lot of times it's due to whatever the native language is of the person that first derived it, came up with the idea, they name it. Sometimes that's the reason. Sometimes it's because they use Latin or Greek or something to name it. Whatever. I don't know where the P comes from.
Maybe they just couldn't use it.
Could be. And sometimes it's because a letter that they want to use is already used, so they use a different one. Okay? All right. So this is change in momentum with time. Or for you calculus people, that's d momentum dt. All right? But we're going to change it a little bit more. We're going to move this t to the other side. And so we end up with our final equation that I'm interested in, which is the sum of the forces times the change in time equals the change in momentum. All right? Yes. And this is written many different ways. So let me show you the different ways it can be written. But let me name the two sides first. The left side is called the impulse. And that equals the change in momentum. Okay, impulse does not equal momentum. Impulse equals the change in momentum. How much the momentum will change. All right? All right, so we got this idea of momentum. All right, let's talk about our units quick. This right here is a vector. This right here is a vector. That means that the vector on this side has to be in the same direction as this vector on this side. So if you have an object, whatever the object is, say it's you, and there is a force on you this way, force number 1, there's a force on you this way, force number 2, the net force then will be the addition of these two forces, which might be, say, in this direction. That means that your momentum will also change in that direction. Now, does that mean that you will go in that direction?
No.
Not necessarily. Okay? Like, for instance, if you have a car that's traveling this way with a velocity, and you apply a force to it this way, an impulse, its momentum will change towards that way. So what will that do to the car? Slow it down, and it may eventually stop it, and it may eventually turn it around, right?
Depends on the force.
It depends on how big the force is and how long it acts, okay? Depends on how big the force is and how long it acts. So let's talk about this impulse for a second. How can you get a big impulse? If you want a big impulse, well, it's F delta T. So you could do
Increase force.
a really big time. Or you could do what? You could really do a huge force. Otherwise known as the way you drive your car versus the way your grandparents drive their car. All right? Is it possible to get on the interstate by slamming on the gas all the way to the floor and accelerating over a short period of time to get up to cruise velocity?
Yes.
Sure. Can you also do it by barely touching the gas pedal? But how long does it take?
Forever.
Forever. Right? Forever.
And then the lights come back.
Hey, I got a question for you. Let's say that you just happened to fall off a building.
Just happened.
What's with all the...
Suicidal thoughts.
Yeah, what's with all of us dying?
Okay,
First
the
we got
economy
hit
is
by
bad
a car,
because
and
of
now
us that they die.
We're not
we
dying.
drove off a cliff. and now we're just
baseball.
All right, some of us here with squeamish stomachs don't want us to die. So, how are we going to keep ourselves from dying?
open a parachute.
Haha. Let's use impulse.
A stunt thing.
Mattresses.
A stunt.
As we fall, is there a force on us?
Gravity.
Gravity. Does gravity act over a period of time?
Yes.
So does gravity give us a change in momentum?
Yeah.
Which way?
Same way, down.
Downward, right? And so when we get right here above the ground,
It's over.
Like a minute.
we have a momentum. And our initial momentum is downward. Right before we hit the ground, we have a big momentum down.
You roll.
Then you bounce back.
Yeah, that kill you.
And then we land.
And then you roll.
And what's your momentum after you land? Zero. So do you have a change in momentum?
Yes.
Ooh. Which way is our change in momentum?
Down.
Negative. It's negative.
Oh, positive because
Well, it depends the direction, right?
Which way are we going to call positive?
Depends, up or down.
We're going to call up positive?
Yeah.
Okay, so if you positive, momentum would be.
You call up positive, this is literally final minus initial.
Final, 0 minus
Our
negative.
final is 0, so 0
A
minus
negative.
Negative, yeah.
Yeah,
a
so it's
negative
positive, yeah.
initial, which gives us a positive. Positive means upward, right? So we need a change in momentum that's upward to stop us, right? That means we need an impulse which way? Up. Which means we need a force which way? Up. So in order to stop us from moving, we need a force upward over a given amount of time. That's our impulse. Now, there are good ways to do that and there are bad ways to do that. Okay? Why is it that if you land on a bunch of pillows, or hey, better yet, you land in a big box of packing peanuts,
Time to land.
or if you land on concrete.
That's fun.
Concrete takes a short time to
Is
land. Packing peanuts takes a long time.
In both cases, you will come to rest. In both cases, you have the exact same impulse, but not the same force. How can you get a different force but the same impulse?
Change the time.
Different amount of time. Because if you had hit packing peanuts, then you get this same impulse. Oops. You get the same impulse, but the force is small, but the time is large. But if you hit concrete, your time is really small, and so the force on you is very large. Okay? That's the whole thing behind an airbag. Actually, also behind seat belts as well. Originally, cars back in the 50s and 60s, the dashboards of cars were made of metal. And so in accidents, they didn't wear seat belts back then, so in accidents, your car would stop, you would continue to move because you have inertia, and then what would stop you? Well, the dashboard would stop you. The dashboard is made of metal, so you would stop really quickly. So you would have really bad injuries. So, how do we make that better? Well, you make the dashboard kind of spongy. Yeah, out of cotton. Or they make it out of like this foam stuff now, right? But they also had you wear a seatbelt. Okay, seatbelts are designed to stretch. Okay, by the way, if you've ever been in a big accident, you need to swap out your seatbelts because your seatbelts will have stretched. And they're designed to kind of break apart a little bit and stretch, which gives you extra time to stop. Now, you'll get bruises where that seatbelt is, but you won't be dead. Yeah. Well, yeah, actually, yeah, that's right. One here, one here, one here. Actually, that sounds silly, but in NASCAR now, they have a head restraint system. Because what happens is they have a 5-point harness that goes across, and then through to hold you in. To hold you in. But what happens is your head still goes forward.
Swing.
Yeah, and so you get whiplash, and it can break your neck and it'll kill you.
It's kind of like a spring almost.
Yeah, so what it does is you got a helmet, it's got like a little tether, and then if you're in an accident, it keeps your head from going too far.
But it's
Your car's on
Yeah, but it lets you move your head around.
feels like
My car's on fire.
Just spending like an hour.
Oh yeah, it would be almost the same. You just go to the end of the string and then
Stupid, he
snap.
says, oh, my head's still in the The car's already exploded by that time.
All right, so like this is the difference between like jumping off a bridge with a bungee cord and jumping off a bridge with a rope. Now you see that in the movies though. You see in the movies, you see like people jumping off buildings or whatever and they're hold to a rope and then they hit the end of the rope and they go, ah, but they hang on. Dude, you're not going to be able to hang on. Now if there's a bungee cord, you could because the bungee cord will extend the time so the force is less. But if you're trying to hold on to that rope snaps, right? And then small time and your hands won't have enough friction, or if they do, you're going to burn all your skin off trying to stop yourself, right? Ouch. So let's say that you're a fireman and you're in this building and you don't accidentally leave the building. The building's on fire, so you leave the building, right? Because you're going to save yourself. How do you hit the ground so you don't kill yourself?
You roll.
Yeah, what you do is you don't land like this. Right? Because then if you land like that, you're going to stop really quick and your bones are going to break and it's going to be very painful.
Guts are going to come out your
Roll off the building.
Yeah, what you do is what they do is it's called the fireman roll actually. What you do is you'll have your feet like this and you point your toes and when you hit and you flex your knees and when you hit you flex down and you throw your weight to one side so that you hit and then roll out. So you turn your momentum instead of stopping your momentum. And so when you're through with the roll, you may have twisted an ankle, you may have even have broken a leg, but you're not dead, right?
The leg's also supposed to be separated because that's what they're
Yeah, I think because if you do this, sometimes what happens is you'll snap your ankles. So you have to keep your feet apart just a little bit. Yeah, so you've gone parachuting?
No.
But yeah, anybody gone parachuting? They'll teach you the same thing. They'll teach you how to do this.
No.
I've gone. It's fun.
Is there a maximum height?
Are you
where
serious?
can do that?
Skydiving or parachuting?
Yeah.
Skydiving.
Skydiving?
Yeah,
Yeah,
you
parachute
skydiving.
That's it.
Oh yeah, you know.
If you're in the military, you don't really want skydiving.
Yeah, actually, and in the military, it's really important that they learn to land right because their parachutes are designed so they come down fast. Because when you're in the air,
Get shot.
Besides, they have a bunch of gear strapped to it.
plus they have like 150 pounds of gear on their back. Now, what they do most of the time is they'll have the gear attached loosely to them so the gear hits before them so that they don't have to land with all of it on their back. Because that's really,
They actually have it strapped to a leg. My brother's gone through airborne.
yeah. So that, yeah, strap down so it'll hit before they hit so they don't have to stop the weight themselves. And they learn how to hit, and when they hit, it looks really bad. They hit and kind of like do the sprawling roll out. Well, what it does is it allows them to not stop all their momentum and have such a great change in momentum. What they do is they just slow their momentum down and then roll out to stop the last bit of it. And it's really nice. You can jump from a 2-story building no problem all day long if you learn how to do that.
2-story?
2-story. 3-story,
You're pushing it.
you're pushing it. But 3-story, you can certainly survive. 4 stories, yeah. You can.
So there's a max height that you can't do that?
Yeah. You get to a maximum height where you really can't. You're gonna.
Like, so you
The momentum change is too great. Yeah.
Don't jump off the Empire State.
Like if you jump like into water, I forget what it is. It's like about 160 feet, something like that. Your speed becomes so fast that even if you pencil in that the water has so much mass, it can't physically move out of the way fast enough when you hit it, and the change in momentum for you will be so great over such a short period of time, the force is too big and it will probably kill you. Oh, by the way, everybody, this business here is huge, all right? This is why you have safety devices in your car, like airbags. Seatbelts stretch, but airbags give you even more time to cush and save you. You can take a car. I do not recommend this. I'm not telling you to do this as a field trip. But if you were to take my car and drive it into a brick wall at 40 miles an hour, 50 miles an hour, if you have an airbag and you have your seatbelt on, you probably just walk away. Okay? If you don't have a seatbelt and an airbag, not good.
And if you're going faster, there's still a seatbelt airbag.
Yeah, there is a limit to how fast you can go. But 40 miles an hour, really not that big a deal. You might get some injuries, but you'll walk away from that. All right. This has to do with shoe design. Ooh, shoe. Let me see your shoes. Anybody have the shoes with the springs? Anybody have any shoes with the springs in the heel?
Mine light up.
Mine has something.
Mine has something.
I think it's so.
All right. Tennis shoes are designed to be springy. Why? So that if you're running over and over again, you don't want a large force. You want a small force. So when your heel hits, there's a time for it to cush and then go back out. You want a long time. All right? Here's something you can do at home. Get a fitted sheet. You know what a fitted sheet is?
Yeah.
It's a sheet that with the elastic that fits around a mattress. Okay, get a fitted sheet. Have 2 people hold the corners of it so that it hangs down with it kind of cupped out at the bottom. All right? And then you take an egg. And I want you to throw it as hard as you can into the sheet.
It's not going to break.
You can't break it. You physically can't throw it hard enough because when it hits the sheet gives. And the fitted sheet is because the fitted sheet will catch it in the bottom. Okay, I was at a baseball game one time. And when I was at, yes, really, one time. No, when I was younger. And when I was younger, I was in high school, I think. High school or college, I don't remember. But I was watching the baseball game, and it was in St. Louis at Busch Stadium, and somebody hit a ball to the outfield. Okay? So here's the outfield fence. The fence at the time was like about 12 feet high. which is a pretty high fence. And the ball came, bounced, and came towards the outfield. And the person in the bleachers leaned over to grab it. Well, they leaned a little too far. And so they flipped and landed flat on their back like this. On the warning track. Now, when they landed and bounced. Okay, here's my question. Would it be better for the person to fall, land, and stick, or for the person to fall and bounce?
Because energy's lost.
Let's move it.
Bounce.
You're not gonna do it
No,
like
you
that.
stick. Because if you're bouncing, means that you have enough force to repel out. And if you just stick, then you just stay flat.
All right, say it again.
If you bounce, that means you had enough force to bounce off. But if you just stuck, you didn't have a lot of force, so you just stood there.
Okay, talk to me this way. Now, let's talk in terms of impulse, okay? Listen, everybody. If you're falling, this person right here, they start with an initial momentum. When they hit and stick, they just stop. But what if they hit, stop, and then bounce back up? What's their final momentum now?
Positive.
Oh, no, it's a positive momentum. And what's their change in momentum now?
Positive.
Well, bigger than that, right?
Yes.
Okay, here's the deal. Here, I'll ask you this. If I throw an egg to you and ask you to catch it, okay? All right, if you catch it, just stick your hand out like this and catch it. It'll probably break, right? Because of force on it. Yeah, how do you catch it? You catch it like this to increase the time, right? Okay, if you hold it like this, it's going to hit and probably break. But what if, how much force does it take to have the egg hit you and then stop it and then throw it back? It takes even more impulse, right? Sure. So bouncing actually requires more impulse. Momentum is a vector. So think of it this way. If I have a ball coming this way, it hits and bounces off this way. If it's a mass m and a mass m here, and this is a velocity here, and this is a velocity here, what's the change in momentum? Doesn't this have an mv here, and doesn't this have an mv here? So aren't they the same?
But what's going slower?
What's going slower? They're both moving.
Velocity is a different.
Yeah, you're going different directions.
Velocity's a negative.
The key is that velocity is a vector. Is this velocity the same as that velocity? So was there an impulse? Yes. Okay, the question is what kind of impulse? Well, here's my velocities. This way, and then this way, and this way.
Define what's up.
Did the x velocity change?
No.
Did the y velocity change?
Change direction.
It changed direction. So which way is the impulse? Is the impulse in the x direction or the y direction?
Why?
It's in the y direction. There is a force upward. There's an impulse upward to make it turn around and bounce up. Does that make sense?
Okay, so then what would it? So would it be better to bounce?
Actually, for that person, it would have been better if they had hit and stuck.
It's like
Now,
Because it was 12 feet only.
Well, the deal is that assuming that the time of impact is roughly the same, to hit, stick, or hit and bounce, then the force had to be greater to make the person fly back in the air. So it was pretty bad. The person hit, and the outfielder ran out there. The person actually caught the ball, but then fell out. And then when they hit the ground, they hit, bounced, and then the ball rolled away from them. I know, sad. The outfielder runs out there and then calls in the medics. They come out there with a stretcher, pick him up, put him on little carts, drive him off. And as he's driving off, the outfielder goes, "Hey, wait!" Picks up the ball and sets it on the stretcher with him. So he did get the ball, but
On the positive side, he got the
yeah,
ball.
he did get the ball. Yes.
I know, if you keep messed up, you do all that and you don't get the ball.
I know. Okay, next time we're going to finish up our ideas of impulse, and then we're going to talk about what happens if there is no impulse. Okay?
You don't stop.
Yeah, if there's no impulse, there's no change in momentum, or no net force, one of the
Lose all
two.
your mass.
So if there's no change in momentum, we have conservation of
No
momentum.
time.
And we're done. See ya.